All right, so yeah, fail one. Never mind. Okay, so.
Okay, great. So my take is going to be the last talk of the session, which is on how you shadow data in the JVM.
All right, so I won't keep you too long. You probably want to have the lunch already. So the what in what, shadowing what in what. This is the heap, and there are some objects that are being born. And then some of those objects die, and we are the analysis, and we want to keep this. For each such heap object, we want to keep some additional metadata or shadow data for this object. Now, why would we do this? Because I mean, keeping more data, okay, at the field, no problem, right? Well, no, because we're writing a dynamic analysis. I hope everyone is quite certain what this means, and you're either just measuring something for a running program, or you're analyzing something for a running program. So the motivation here is basically that we are writing a dynamic analysis. We have the full access to the program. That means to its memory and also to its code. And we want to store some additional data for each heap object. Now, the question is, which of the analysis might want such a thing? And let me start by saying that all of the talks before me need some form of storing some additional metadata. If I understood correctly, you're probably storing basically per class metadata.
No, I'm not actually. I'm just pushing that out onto disk, so it's inverse.
All right. But
and then I'm reassembling that, but
I see. All right, and here it's really per object metadata story. So some examples are, you're keeping track of how long your objects live. So whenever an object is born, it gets its metadata. That is the timestamp of when it was created. And then when it's dying, you just look at the timestamp and you know for how long it lived. Another example is, you're looking at data structures, recursive data structures, such as linked lists, graphs, and trees, for example, on your heap, and you want to track when you're looking at a single node of such a structure, you would like to access some information about the whole data structure it belongs to. So for this reason, you might just keep as the metadata the reference to the structure description, let's say. So Java can leak memory, as you might well know. If you're keeping a reference to an object but not using it, you have just created a Java memory leak, congrats. And an analysis that would be detecting such memory leaks would be basically keeping track of when was the object last accessed. And then you would just look at the whole heap, and whenever you find an object that was not accessed for a long time, you might pop up a warning flag, this might be a memory leak. You might be wanting to keep track of which objects are covered with which locks, and then whenever you see a breaking of this protocol, you might say, oh, that might be a data race. You might be looking at the information flow inside of your program, and whenever you see a piece of data, for example, that was being downloaded from the internet, it is being tagged by this metadata as unsecure, and it's going to be executed. Your dynamic analysis again says, wow, something bad is happening here. So this is what analysis might want to do with metadata attached to heap objects. Now, what exactly? The first and basic requirement is the ability, here I am the analysis, here is the object, and I want to store this metadata. I want to attach this part of metadata to it. And then retrieve it, of course. We don't want to lose this. Then we would like to be able to walk the whole heap somehow, and to get basically a repository of all the objects that have this metadata and collect these metadata. And finally, whenever an object dies, we want to receive the metadata for the final time. We don't want objects dying and we would not be able to get to this metadata. So I'll describe 3 basic ways, out of which 2 work and 1 is just terrible. But it's not terrible because it's the best one actually. The best approach would be your analysis should be able to really add the field to the object. Now here is a caveat. You don't want to add this new field to each object, because then your analysis would have to say, oh, I'm looking at an object. Does it or does it not have the metadata? How do I tell? Do I do instance of? That is quite costly. We would like to have a guarantee that every heap object that we see in our analysis has the metadata and that we can access it. For this reason, it's much better to just put this new shadow data metadata field into the object, just the Java-lang object itself. Now, no, not really. I mean, if you're okay with interpreted mode, then you're fine. Otherwise, once you try to JIT compile this, all hell breaks loose. So not in Hotspot, sorry. But imagine that it works in a future version of Hotspot. They have fixed their constants, and now they were able to survive an object that is of a different size. So for the shadow data, we can just use this field, and we're perfectly fine. If we want to enumerate all the objects, we have to have our own weak collection of all the objects, and we have to keep track. And if we want to be notified whenever an object dies, we need, well, the reference key. Approach to hash map. This works. So there is one huge hash map in the memory, or let's say big. Its keys are the objects that we're tracking, and its values are the shadow data. Well, this works. We have to synchronize it. In our experiments, we have been using just one lock for this hash map. But you can use a concurrent hash map if you want. We did not do this. Now the important parts are these. First of all, it has to be a weak hash map. Otherwise, you're still keeping track of your objects on the heap, and nothing can be really garbage collected. And second of all, you must never ever touch the hash code of the objects that you are tracking in your analysis. Several things can happen. It can have side effects, by which I mean bloat really crashes when you touch some object's hash code, or it can just not work. It might be implemented incorrectly. So you need to be using in your hash map really the system identity hash code. Yeah. So put get deals with the storage and the retrieval of the shadow data. Map values gives you all the objects that you're tracking. Beautiful, perfect. And you still need a reference key. Now for the last approach, there is a special secret API, or a secret but special, in the JVM-TI that allows you to do storing a number, value, in the object's header and retrieving it. Now this is a 64 value, whatever, and we can just create a global reference to our shadow data in the native code, cast this to a 64-bit value, and store this as the tag in the object's header. So you can see here that there is the object. It's storing the tag, which is a pointer to the global reference, which is this global reference, I might add, is the garbage collection route. It is really a data structure inside of the JVM, and it's basically pointing to the shadow data object, and it's keeping track of it even if this moves because of the garbage collection. Yeah. So the JVM-TI API gives us the set tag and the get tag. It's nice enough to give us a heap iteration method. We can just go over all the heap objects, and now comes the best part. We can say that we want only the tagged objects. So we're really getting only the objects that we're interested in. And it's giving us an event. Whenever an object is garbage collected, we retrieve its tag for the one last time, and we can traverse this to our shadow data, and then process the shadow data and garbage collect it. By garbage collecting, I mean we get rid of this global reference. Otherwise, we would be, having all the shadow data on our heap, not being garbage collected. Whoa, memory leak on our own. Now, yeah, as I mentioned before, field does not work in Hotspot, which is kind of, for us, it's a big deal. Hotspot is the most prevalent and so on. Heap tagging, unfortunately, only works there, so it's like midway, and hash map, it just works everywhere. Yes, it is slow. So we created simplified leak detector to showcase these two working ways and compare their speed. We are comparing hash map and heap tagging. we are running this whole leak detector on DACAPO benchmark suite and several different environments to be able to compare. And our metric is basically the end-to-end time of running this benchmark suite with our leak detector. The leak detector works as follows. You keep track of the last access time and the creation time for each heap object. It's based on the SWOT leak detector. So whenever an object is created, you store the object created. Whenever a field or a virtual method is invoked on this heap object, you store the last access time. And finally, in intervals, you go over this list of all objects and you find the memory leaks based on some predicates. Now the results are the following for you. Let's see. These are environments, 3 different. The baseline time, this is the uninstrumented DACAPO benchmark run. And these are the times for the hash map approach, and these are the times for the heap tagging approach. You will notice that this is the J9 virtual machine, meaning there is no heap tagging. So the slowdown, 50 times slowdown with the hash map, 90 times slowdown with heap tagging. Now this overhead looks quite huge. Why is this? If you look at the breakdown per benchmark, you will notice that the benchmarks that are using multi-threaded, that are multi-threaded in the DACAPO, have higher overhead in both hash map and heap tagging approach. Now this is because, of course, we have one hash map for the heap tagging, and we are synchronizing on this one common shared hash map throughout the program. In heap tagging, actually the story is quite similar. What they're internally using in the JVMTI implementation, they have the same thing basically. There is yet another hash map. There is one shared block. There is one shared block. And even for creation of those global references, there is another hash map with another global block. Now, this is basically, you start with the full implementation. So this is heap tagging, leak detector, and you start stripping away features until you get to the uninstrumented program run. Now, this is basically saying that we get rid of features in steps, and the time to run is going down. This is nice, and there are some jumps. For example, whenever you start processing all the object allocations and accesses, your time will go up very sharply. So the overhead of just having the instrumentation in the Java agent is quite small. The overhead of calling the JNI is quite small. The overhead of garbage collecting the references, the global references, is quite small. And the actual overhead here is incurred by the fact that whenever there is an object created, we have to create this new shadow data, we have to update the shadow data, and so on. So to conclude, there are a lot of dynamic analyses that are required to store per object metadata. I have shown you that the way to do this on Hotspot currently is not by using heap tagging because it is too slow, not by using field because it will crash once you JIT compile this code, but actually by the simplest possible imaginable approach, which is using one weak identity hash map. Now, we have made our work public, open source, so you are invited to go to this address and download the implementations to compare the shadow data implementation in the hash map. Very simple. You will see also the leak detector there with the heap tagging approach. But really, just go and use the hash map. Thank you.
Hash map per static class.
For static class.
Per static class.
Per static class.
Separate hash map per
Yeah.
static class.
We did not. It might help.
If I followed what you said, you were saying that the actual hash map is a bottleneck,
Yes.
but you had a single lock per
Yes.
structure. Could you do per bucket locking?
Yes, of course, we can just pick concurrent hash map and it would be much better. From the options that are currently available, you should not be using heap tagging because what they do internally inside the JVMTI implementation, there is a simple hash map just as we use. So you will be much better off without any concurrent hash map, just a simple weak identity hash map will do much better than the alternatives.
So actually, I have two questions. The first is just related to JVM TI. So, given the performance overheads they're having, this is obviously not the use case they had in mind when they designed that interface. What did they have in mind, other than, did they have specific kinds of applications and you're just trying to do something?
I'm not certain. I would have to speculate. The way to do this correctly, I believe, the thing is, in JVM TI, the heap tagging is implemented basically by having the hash map there.
Right.
From the object to the heap tag. Well, the right thing probably might be to just take this tag and store it in the object header. As the right way to do this in pure Java would be just to have one field stored in the object. But for technical reasons, this is impossible nowadays.
And the other thought, in our instrumentation framework, the Roadrunner framework, we don't tackle quite the same problem because we're not trying to do all objects. We kind of punt on anything out of the standard Java outline section. So you're trying to solve a much harder problem. But one thing that we found really useful to get around something like the bottleneck on the data structure map, this map, is to actually use inline caching, per thread cache at each access location. Have you thought about doing anything like that, or do you think that might?
Yes,
help
definitely.
JVM?
Yes, definitely. It will be much more complex because, of course, there is one thread that is running this. This thread is instrumented. That means that there is some logic that needs to be accessing data from another thread, and now you have to, basically, you're touching a different cache. Still, you have problems.
Right. I guess I'm thinking a per thread cache, so each thread has its own.
Yeah, but the thing is, the thing really is that these threads need to touch each other's data. If there is a shared object, and you have it in two different caches, and you have written something here, and you need to read it here, which is what can happen in a dynamic analysis, then you still have to somehow, flush the cache over here.
Oh no, I'm just talking about caching the table lookup. The result of doing the table lookup, right? So you should always find the same shadow object for.
But what if someone else wrote into this shadow object? You would have to
shadow
write
objects.
throughs to somewhere.
Right. Okay, so again, you're solving a much harder problem than we were thinking.
Thank you.
So I just have a comment. So, did this talk convince you guys to use this? Particularly these two previous speakers?
We are using it already.
Okay.
I implemented the tracing in one night of hacking and coffee. I did not think about anything like JVM TI. I just said, I need to get this to disk. And also my problem is slightly different because I stored a whole trace to be able to later reproduce my measurements with different variations of the algorithm. So I will now consider doing it if I run the analysis online, which should be way faster than what I'm doing right now. But actually I was not so much touching on this problem at all.
I'll just mention that when I was paying attention to your presentation, it seemed that you might be actually needing not per object, but per class.
Yeah.
Now, you can use hashmap, of course, as well. Instead of indexing by the object, you'll be indexing by its class. It's perfectly valid to do it like this.
It would be per method, but it's the same thing. It's like a static.
Yeah.
That would be single.
Per method means that, per object,
Yeah.
and then you
Great, thanks.